thank you for the introduction. I mean that presently, I mean that I'm not associate editor of the Journal of Field Robotics. I mean that chassis was in the previous version, but I'm involved with a lot of, I mean that all the IB and ITSC, I mean that in this area. So what I will be doing is just I will present it a summary, I mean that of the research of my group, but in future mobility. So what do we do? I mean that we're working in automation for urban transportation. I mean that, and we are trying to, I mean that working on technology in order to enable the move of people, I mean that of goods in city. And our current, I mean that focus is on research, work for industry and governance in Australia and around the world. So the idea is that we wanted to demonstrate research outcome with working with real vehicles in realistic scenarios. And although we are doing work in urban vehicles, we are more concentrated in areas where there is significant interaction with people. Okay, so vehicles moving at low speed in highly crowded environment. Let me see. Let me do something. This is something that. Sorry, I mean that I went too quick. I mean that. Just bear with me for a second. I mean that. Okay, so. So this is one of the vehicles that we have. I mean that this is a perception vehicle. I mean that we use these vehicles in order to gather data. This vehicle is retrofitted with 360-degree perception. I mean that and the sort of data that we can take allows us to track everything that, to track and classify everything that moves around us. And this is an example, I mean, that of driving in the city. We keep driving this vehicle every day. We have collected enormous amount of data, and this actually help us to work in many different areas. I mean that. For example, I mean that we created a lot of information, and this has been published in one of the data set, in order to be able to infer driver intention. I mean that, and this is very important because most of the data sets, I mean that present information from infrastructure, and the view of infrastructure is different from the view of a vehicle. And what we did is just we have this vehicle, we parked these vehicles in particular position of runabout, and we got I mean that more than 23,000 trajectories. And this is important because this is a trajectory as it could be seen by a vehicle. So if you get this information and if you can infer intent, this is a real outcome, because if you're basing your outcome on a spatial infrastructure, the spatial infrastructure will be located only in very, I mean, that defined places, and the result will be very difficult to generalize. And in this, I mean, that with this data, we already presented, I mean, that some contribution in the area of trying to infer, just to maintain the probabilities of what this driver could do when they get the intersection. This data is also very useful in order to do analysis of safety. I mean that, so if you wanted to get information about how the driver behave in the road, I mean that is the vehicle behave aggressive or non-aggressive, I mean that you can have a lot of information of trajectories. Okay, so this is what I mean that this is a part of urban navigation. So there is another, that aspect that we are studying, that we related more to smart city, and then we see that these days we have three major disruptive technologies. That one is electrification. So vehicles are becoming electrified. That we are analyzing that full automation, it is really possible in many areas, okay? And people are accepting the concept of car and ride sharing. And it is these three combined together, these three aspects that are the ones that are going to have a profound implication in the way we move. That because we are going to be able to provide clean transportation, eliminate congestion, and also improve safety. But for this, that we need three main components. We need the technology, the investment, and basically we need to change the policies. No, just let me have the sound here. So if you can see, that this is where we concentrated most our effort. That we are looking at autonomy. That demonstrated the concept of autonomous transit on the mind. In this sort of environments, that we are trying to address the aspect of machine-human interaction. What we like to have is seamless interaction between a machine, a vehicle, and people. That we like machines to be able to infer the intention of people, and we would like that the people to be able to infer the intention of the machine. Also, we are, as you will see, we are looking with multi-purpose platforms. That the idea is that we can have this platform, that during the day moving people, and during the night performing different tasks like moving goods or cleaning the facility. And this is the sort of presence that we are looking at. that university campus, construction area, the other one is the Olympic Park, that and certain urban facilities. And as you can see, that in this video, that we summarize a lot of the activities that I'm going to be presenting. That in this case, that the vehicle operating autonomous. That in this case, the vehicle is detecting the pedestrian, but the vehicle is also seeing the pedestrian through information that is available, is coming from a special infrastructure. And the idea here is that we are looking at demonstrating the aspect of getting a person from one place to the other. And the fundamental idea is that in our university, like many universities around the world, investing a lot of money in buildings, and we need to see how this technology will work in this environment, because in the next 10 years, that this technology is going to be fully deployed, and in places like University of Sydney in this case, but many universities, we may not need any driven vehicles. That you could have all these vehicles fully deployed and using the concept of electrification, that ride share and everything, that it will sort out many current problems. So if you look at our strategy, that we have a number of projects looking at autonomy. That autonomy based on the sensor retrofitted in the vehicle. We have also doing a lot of work in vehicle-to-vehicle communication and vehicle-to-infrastructure communication. We are looking a lot about doing research in the area of intelligent infrastructure that is retrofitted with cameras and lasers, they will be able to track people. And in this case, that this vehicle is becoming completely aware of what is happening around the corner. Okay, So, and at the same time, we are looking at addressing these problems in a scenario of complexity that is actually increasing. So just to give you an idea, I mean, that we've been working with some of the projects for more than 3 years, and we started to work it in park areas. We moved to University of Sydney, and now we are basically moving to areas that combine areas of a different level of complexity. And at the same time, there is a lot of work in order to change the behavior of the vehicles when they move from one area to a different area. So probably we'll be able to talk more about this. And in order to work in this area, I mean, that we usually concentrate on robustness. We don't want to work ourselves, I mean, that develop algorithms and test it with a particular data set. I mean, that we're interested in robustness. I mean, that, and something that we did is in a particular area, I mean, that combine different type of complexities. We generated the data set just taking, gathering information for more than 18 months. And we were driving every week. And we're driving every week in an area that consists of some public road, very heavy, a very large number of vehicles. I mean, that the areas that they go in the underground car park and so on and so forth. So this database has a lot of complexity. It have complexity in terms also in how the different season change the campus. So also they have complexity. For example, you can see in all these yellow buildings, I mean, that that has been a lot of constructions. I mean, that if you wanted to test, for example, localization algorithms, I mean, that and you build map, I mean, that then you need to, you realize that you need to implement updatings of the map in order to be able, and you can test all those things. So this data set is available, and perhaps we can talk more about this. So this gives you an idea, I mean, that what we mentioned, I mean, that if you wanted to achieve these goals, I mean, that which are the stakeholders that you need to get involved? Okay, well, we need the technology, the smart of technology, and for this we need probably researchers, I mean, that, and we need the companies that are actually providing this technology. We need the investment coming from the university, the government, and companies, and you need the smart policy, and that's why we need we have the transport agencies involved with us. So we are demonstrating the things to them. We are demonstrating to them what need to be changed, okay, in order to be able to deploy this technology in real life. Okay, so this is interesting as an introduction. Now, what we are start talking about the fundamental work that we are doing. I mean, that first thing that we need to answer. I mean, that and perhaps this summarizes the activities and relate to all the previous presentation. What is needed for autonomous driving? Okay, the first thing that we need to do is just to solve where am I? Okay, so this is basically the localization, and there has been a lot of work, and I mean that and obviously, I mean that although we've been working for the last 20 years in this area, I mean that this is not the sole problems. I mean that and there are many techniques, and one, it's not a sole problem when you wanted to get a vehicle and assure localization. I mean that with robustness. I mean that we wanted to get to all these trajectory that I present. I mean that and be able to localize 100% of the time every day on the year. So one of the things that you can do is just basically build maps. I mean that future lines. I mean that whatever you want. And then, I mean, that in addition to that, I mean, that to have the process of building a map, you need the process of map maintenance. I mean, that you can build a map, I mean, that and you can operate for the months, for a month, and then all of a sudden, I mean, that things change, I mean, that and your map need maintenance, I mean, that in order to operate. Huh? Sorry, I mean, that this is long term. Then when you solve the localization, I mean, that the next thing that you have to solve is understanding the scene. I mean, what is around you. I mean, that, and for this, you have all the sensor information. And then you have to fuse it. I mean, that do a probabilistic integration. And then when you fuse it, I mean, that then you can do all the real tasks like start tracking all the objects that move, semantic, and do everything. And then the next step is what happened next. I mean, that when you have all this information, you have to take a decision and doing control. Okay, so this requires, I mean, that all these areas of research, I mean, that first of all, as well, what is the platform that you wanted to do, to work? I mean, that what is the best platform in order to address your problem? You need to do perception and understanding. If you are going to interact with other driver and pedestrian, I mean, you need to look at intentions. I mean, that you need the localization, I mean, the map maintenance and path planning and control, cooperative perception, and safety assurance. I mean, we have, I mean, that groups working, I mean, that or number of people working in all these areas. And I will try to summarize the work in some of them. I mean, that first of all, this the vehicle platform. I mean, that this was, I mean, that I mean, when we started working, I mean, 4 or 5 years ago, I mean, that with a company, I mean, that and we established a very good relationship. This was the original idea. I mean, that can we generate, I mean, that a basic platform that a platform that could be changed, I mean, that in very little time, in 15 minutes, I mean, that and to have different operations. I mean, and this was the original idea. I mean, that this was the first prototype. I mean, that we've done most of our work with these vehicles. They are very sophisticated vehicles. I mean, that this is based on this platform. And just to give an idea, I mean, that we work, I mean, that with them for a couple of years in order to design, I mean, that the process in order to have this machine to be computer control able. I mean, that, and just to give you an idea, I mean, that this is the current generation of machines. I mean, that, and you can see that they're much more appealing. I mean, that, and probably this is one of the companies that this is the leader in the work in order to provide this this platform. The idea here is that you have this platform, and then on top of it, you can put whatever you do, and you can transform this in a few minutes. Okay, so you can see that there is a lot of research work in the platform. Then, I mean, that if you look at the part of perception and scene and understanding, I mean, that, and basically, I mean, that, okay, all the vehicles, I mean, that, or most of the research work is based on cameras and laser and radar. I mean, that, and when you look at the fundamental problems, I mean, that, okay, I mean, that cameras will give you they're low cost, I mean, that they contain texture, I mean, that they have high resolution. On the other hand, I mean, that you have LiDAR, I mean, that that can give you range, but in general is much less resolution. I mean, that what you wanted to do is just basically integrate both information, I mean, that and use the best of both worlds. I mean, that, but there are fundamental problems. I mean, although theoretically this is good, I mean, that you have to solve a number of challenges. I mean, that, and one is that, okay, I mean, that when you wanted to integrate cameras with laser, you need to do the calibration. I mean, that you need to be able to get the right, the relative position of cameras and laser with very, very small error. I mean, that, and we'll talk about this. You need to synchronize the information of some of the sensors that are much slower with respect to the movement of the platform. And you need to look at the occlusion handling, okay? That this is very interesting. And you can see, I mean, that something here, I mean, that here we have the camera and we have the laser. I mean, that this camera is located very close to the laser. So they have the same vantage point in order to see the image. And you can see the different type of laser here that are very far from the camera, although they both can see the same thing, but they're seeing this from the different vantage point of view. And this may create different problems, I mean, that depending on what you want to do. And we have an example, I mean, that later on, okay? So with respect to calibration, I mean, that, and calibration has been a problem that has been investigated all around the world. I mean, that, and what you have, I mean, what you do is just, you develop algorithms in order to just look at the calibration patterns. I mean, that you take different samples and then you apply an algorithm. I mean, that in order just to get the relative translation or rotation of laser with respect to cameras. What people do is just take a large number of images. I mean, that then what happens is that you're working for 2 or 3 years, you become an expert and you know how to select the proper image in order to get the best result. I mean, that then this person is gone and you lose expertise. You try to duplicate the result and you cannot duplicate the result. What we did is just generate a number of publications in order to be able to make this process completely automatic. I mean, that the idea is that, okay, try to encode the expertise of people. I mean, that you can say, well, I mean, that this is the way to calibrate. You take, you look at patterns with the camera and laser. You take, let's say, 50 images, but how you select the best combination, okay? So, and we provide the algorithms in order to do an automatic selection. And these algorithms are also giving you the most likely error in each of the degrees of freedom. I mean, that, and also present, I mean, that an actual view of the scene. So the idea is from a number of images, I mean, that even if you don't have expertise, I mean, you take 50 images and basically the program automatically selected the one of the best configuration and actually they show you result. And then in this image, you can see that, okay, you can select, if you select any 3 combination in this area, you can get result like this. I mean, that, but if you select, I mean, that one of the good combinations, I mean, that you can guarantee that you get very good results. And this is basically the expertise that is usually encoding the people that have been working for a long time. Okay, you get these algorithms without the experience, and you can get something like this. So, and this is very important. I mean, that if you don't get the extrinsic calibration right, it's very hard, I mean, that to get any consistent result in order to infusing laser and cameras information. Once you get everything right, I mean, that then you can fuse, you can stitch image together, I mean, that and then superimpose the laser information. The other aspect that you also have to consider is that in certain sensor like lasers, I mean, that you start to scan in one position, that is a rotation on the laser, and then you end at the different position. You need to consider the movement, and then you need to compensate, I mean, that for the car moving. If you don't compensate, you get this sort of information. I mean, the moment that you compensate, I mean, that this is very good. So, I mean, that, and we have a number of papers, I mean, that published in this area, okay, that it consider this compensation, okay, and usually you do this compensation, I mean, that using the dead reckoning information, but the dead reckoning information comes with uncertainty. So, and we have some paper that in which we actually present the compensation and get the proper uncertainty. So you can say, well, I mean, that this point of the laser is at this position and with this uncertainty. And the other aspect, I mean, that is very important, I mean, that when you are about to design your autonomous system or the perception, is where do you locate the sensors? I mean, that, and in this case, I mean, that you can see that and illuminating the board, and there is an area that the camera can see that the laser cannot see. This is with the view of the lasers here. So if the camera and the laser are in different positions, I mean, that you have the problem that are displayed in this figure. I mean, that this camera can see this. I mean, that the leader can see this. I mean, that and the camera there can, I mean, that not see the same point. I mean, that so this is something that you need to address. Okay, so now let's imagine that we have, I mean, that this problem solved. I mean, that and we would like to basically extract as much information from vision. I mean, that and we use semantic. I mean, that and the ideas, as you can imagine, is that I would like to be able to move this semantic information from the vision domain to the laser domain. Okay. In order to do that, what is fundamental is to have a perfect calibration. I mean, that between cameras and laser. That's why, I mean, that the most critical step is the calibration. I mean, that and having algorithms that are flexible in order to recalibrate, because whenever you are moving a vehicle, the things they move a little bit, so you need to recalibrate. But now let's concentrate on semantic. I mean, that vision semantic is something, I mean, that is fascinating, because it allows to solve one of the fundamental problems of labeling every pixel as belonging to a particular class. And it's fascinating now that we can do this in real time. I mean, that these are network design. I mean, that they're not very accurate, but they're designed in order to work in real time. We can get 30 frames, this information at 30 frames per second. Okay, so I mean that we can actually teach the system some interesting things. For example, I mean that we can make the system to learn. I mean that what is the path that the system has to follow in a non-marker road. So you can do fascinating things. I mean that, and then when you have very good calibration, I mean that you can superimpose this information in multiple images. I mean that, and also infer the parse. So this basically require all the components to be working well. I mean that, especially the calibration. So what happened if you wanted to fuse, I mean that vision biases? So this is becoming fascinating, because what you can do now, I mean that if you have a perfect extrinsic calibration, I mean that you can get a label in the vision domain, and then you can label every point of the laser as belonging to a particular label. And this is a part of our work. I mean that so you can see that we can get each of the points, I mean, of the laser, and we can provide a particular label. And this is becoming very useful. Let's go back to semantic, and one of the things that we are doing is just we did a lot of work in trying to estimate the robustness of a semantic. I mean that so can semantic vision-based semantic work? I mean that and one of the problems people that try to work with them knows is that you can train the model. I mean that you can get the model trained for a particular data set, and when you move to your environment, you see that the system doesn't work that well. Okay. So what you have to do it, I mean that well, I mean that you need to collect a number of images and be able to train. I mean that collecting a number of images and labeling a number of images is very time consuming. And you never know, I mean, that when the system is going to fail. I mean, that, and also and there is another problem. I mean, that most of the networks are trained for a particular camera with a particular vision in front. If you put cameras looking at the side, then you need probably you need to do a retraining. I mean, that, so on one side, I mean, that you know that if you have a set of images, I mean, that and label images you can adapt to your area. This is transfer and learning. I mean, we've done this. I mean, that, but this doesn't solve the problem, because when you look at our data set, I mean, that you can see similar areas, I mean, different part of the day, different part of the year. I mean, that there are so many combinations. I mean, that that is almost impossible to generate training in order to train the network for I mean each particular case if you wanted to do manual label. Okay, so something that we did is just say, well, I mean that is it possible to automatically generate a label? Okay, so and one of the things that we did is just let's try to generate a road label with laser information. Okay, so and this is basically a way to automatically generate a label. Okay, so and now I mean that you can go get any or take any data set. I mean that you take it over here. You run it through a program, it automatically generate one label, one very important label. I mean, that is a role label. And then you can test the network. I mean, that how it behaves. I mean, that in this particular, with against this particular label. At least you know that if it doesn't work with this label, you have a problem. Okay. So, and we have the whole pipeline. I mean, you get the data, you automatically generate the labels. I mean that you generate the semantic segmentation and you compare this. And basically what we did is that we, I mean that tested, I mean that in our data set, I mean that and basically what we did is just we codified the things in the following way. I mean that we put in blue when the vision semantic is accurate in more than 95%, and in green when it is the accuracy is between 90 and 95, yellow 85, 90, and we say that is if it is less than 95% accurate, I mean that we cannot operate. And something that we do is just we get a particular week and we paint, I mean, that how good is this network? Okay, I mean, how good this network behave? And you can see in this way, in this case, is it's mostly blue and green, okay? And but you can find, I mean, that cases, I mean, that in automatic manner in which there are many reds, okay? Whenever you find that something that you can do, whenever you find something like this, I mean, that you can say, well, there is something that I need to retrain here because this has been a particular bad situation. And then you can retrain and you can improve. So, and never in the interesting thing that everything is actually happen automatically. Okay, so you don't have to do any relay. That is a paper that we published, I mean, that 1 year ago in this area. So when you look at the automatic labeling, is something that is very important. Okay, so which is our next step? I mean that. Okay, so this is the actual quality of our real-time networks. I mean that it's okay, but these days you can do instant segmentation with very high quality. Okay, so we can start thinking about that, applying this. Obviously, this algorithm has to be applied offline, but the quality is very good. So even, I mean, that in order to detect people, and you can see that they discriminate a lot. And this is an interesting source of information. And this is basically the same video that is running. By no means we can do this at this speed, but this is never going to operate in real time. This is basically important in order to generate labels for testing. Okay. The other area that is really fascinating, that is the part of image-to-image translation. I mean that this is a paper that originally came out from Berkeley AI Research Laboratory. I mean that that idea here is that we've been used to go from the image domain to the semantic domain. The question is, can we go the other way around? Okay, so can we start from the semantic domain and create an image that doesn't exist, because we can tamper this image, we can create new labels here, okay, and we generate the different images. I mean, and this is something very interesting. I mean that, and as you can see, I mean that some of the image in this paper that they started with the images that don't exist. It's not very accurate, but it's accurate enough in order to test your algorithms. And this is basically part of our work that we started with some semantic, I mean that, and we obtain, I mean that images that don't exist. And also something that we can do is that we can start working, changing the appearance. I mean that we can, if we have this image, we can teach the system, I mean that how to generate the same image but with the different appearance. And this is very interesting because if we can change the appearance, okay, all of a sudden we have a night image and we have the real labels, okay, because I mean that the image is still the same, no? Time changing the topic now. I mean that let's look at the area that we are working is human-machine interaction. I mean that this is the part of pedestrian position and intention. I mean that when we are working with people, I mean that the things that the problem that we need to solve, I mean that are very different. I mean that because we are always interacting with people. I mean, and what happens is that people behave very different in the street that in this type of environment. Whenever they're working in this environment, they're more empowered, they are in command. When they are in the street, I mean that they are obeying different rules. I mean that, and why it is problem, I mean that this is a video taken by our vehicle. I mean that you can see the people, I mean, that it's not always looking at you, it's not always, I mean, that paying attention at the vehicle, I mean, that so you need a different type of interaction. You need to be tracking not only the position, but being able to infer the intention of the people. I mean, that and what you are trying to solve, I mean, that is this sort of a communication that is implicit. I mean, that currently this communication happen in many different ways. I mean, that the pedestrian, I mean, that infer intention from the vehicle by the way it moves. I mean, that the way it changed the acceleration. I mean, that there is sometimes communication eye-to-eye contact. I mean, that so the idea, I mean, that you can see that there is a lot of things going on. It's not just object tracking and planning. Okay, so when you look at the intention, I mean, that we are looking at the people, but we are looking at the pose. Okay, what can we infer? I mean, that from pedestrian, this is also from our data set. I mean, that sometimes we can even infer, I mean, that the head direction, and sometimes we may be able to infer that if these people, the people are actually using a phone. I mean, that this is very important because this the behavior of a pedestrian if is using a phone is very different from the pedestrian that has some level of attention. And you can see that there is a wide variety here of how much aware are people with respect to, I mean, that the vehicle. The other aspect is the trajectory prediction. I mean, that with the tracking, we have the past event, the yellow. I mean, that and we would like to be able to predict. We would like to be able to predict where is going to be this person. I mean, that when the vehicle is at this position. And for this, I mean, that we had a lot of work that consider the interaction. I mean, that and what we're trying to do is that to get a probabilistic view of where the pedestrian is going to be. I mean, that and we know that sometimes the pedestrian can do multiple things, and we like to be able to know which are these multiple things that there are multiple trajectories that the pedestrian would like to do. And that's why we work probabilistic. And let me show you some of the examples. I mean, that we have the car going behind, and you can see all the potential, I mean, the trajectories of the people. And this is what we need to know. Then eventually the trajectory, when you get closer, I mean, that they all fuse together. But we need to know, we need to be able to have all the potential trajectory in order to do a safe plan. Then the next question that we had to ask is just, well, I mean, that if we wanted to work beyond the line of sight, I mean, that how can we develop the technology and the algorithms in order to move information, I mean, that among vehicles. This is the part that we are doing in vehicle-to-vehicle communication, okay? Let me go quick here, I mean, that the things that we are trying to do, I mean, that
can you hear me?
I mean, that is that on one of the aspects is as if we have a special infrastructure, the special infrastructure is actually seeing the people, then
I don't know, maybe there's some
move this information to all the vehicles.
Yeah, maybe he cannot.
And then the other aspect, and this is a rather simple problem because the special infrastructure is at the given location.
Sorry, Wendy.
With a very well-known uncertainty, but we're also trying to solve a different problem. I mean, that when we want to fuse the information from the special infrastructure and from a smart vehicles, I mean, that the smart vehicle may be seeing this person, I mean, that but the smart vehicle, we have an uncertainty. This has much less uncertainty. How can I use the information of this vehicle and this vehicle? So this vehicle is getting update from that there is a person here from all the information coming around. So, and this is created some complexity in order not to reuse the information, in order to make the information consistent. We have also done a lot of work, I mean, that in order just to think about the future, imagine that the spatial infrastructure is fully deployed. And then you can imagine that if there are a large number of spatial infrastructure, can you implement autonomy in a vehicle without sensor? I mean, that, we've done demonstration of doing autonomy with information coming from a spatial infrastructure. So the idea is that the spatial infrastructure is tracking all these projects, and then the path planning of this vehicle is based on only the information of the spatial infrastructure. We have some videos of the operation, but I think that I'm really running out of time. Okay, so I will stop here. I mean that, and I may attend some question. Let me see if I can stop the sound here. Yes, and I'm ready for questions.
Yes. Anyone who has questions, please just ask.
I guess prior to that, Eduardo, can you hear us? Can you hear us right now? Hello?
Hello, yes.
Can you hear me?
Okay.
You can?
Yes, yes,
oh,
I
okay.
can.
Yeah, because there
Okay.
was some sound problem, and we thought you cannot hear us due to some reasons. But I guess we're kind of already out of time for 4 minutes. Maybe, yeah, do you have a quick question? Otherwise, we can just move forward.
Yes, so maybe I will just ask a very simple question. So this is very wonderful line of research that you covered a wide range of topics. So I think what's the most challenging research problem that you see that we need to like overcome immediately for the smart city to become a reality?
Yeah, this is a interesting project. I mean, interesting questions. I mean that the fundamental problem is how can you assure safety? Okay, I mean that and in any application that they ask me today, I mean that what you are confronted is that the industry or government, they will ask you, okay, can you do a simple demonstration of autonomy? Okay, and the moment that you get one of these vehicles operating with people, it becoming the most complex operation in the world because you have to solve all the problems with robustness. Okay, so, and the idea is that you say, well, I mean that how can you assure robustness? How can you assure robustness in the perception? Okay, so how can, if I'm going to fuse laser and cameras, how can I assure that the scenes remain calibrated? Okay, then I mean that if you can assure this, you know that your algorithms of tracking are going to work. I mean, you know that your path planning algorithms are going to work. Then you say, well, I need localization. How can I assure that the localization is going to work? Okay, so one of the things that we have localization, I haven't talked a lot, but I have a couple of PhD students have finished, one is finishing the thesis now, and the other one finishing the thesis 3 months ago, that it was all about localization and map maintenance. Okay, so when you are operating on the campus, I mean that you can see that all of a sudden you go on the ground and the modalities of localization have to change dramatically. Okay, and then you can say, well, if I'm going to work today, if I'm going to do a demo, I can try 10 times and then I will get it 7 times, and then I will present a video of any of these 7 times. But if the thing has to work 100% of the time, okay, how can you be absolutely sure, okay, that this thing is going to work 100% of the time? Okay, so, and this is the most challenging question. That's why we are generating so much data So if you want to test localization, don't tell me that this is working in the Kitty data set. Just tell me that it has been tested for 2 years of data, all the station, and it failed that many times. Okay, so that's the fundamental challenge.